Hi, in this video, I'll go through an example of a ring. And this example is fairly important as it come out quite a lot in practices. And many people has tried to uncover more and more properties of this ring. So, what is the ring that we're talking about today? Well, we're talking about the polynomial ring. And we'll first start off with some basic definition that you should be familiar with already from all our other examples. And that a polynomial ring is just a set that is written in these formal sums. And what is a formal sum? Well, it's just a notation to denote the following expression. So there's no addition going on or anything. It's just we write it in this way where it looks like a sum. And the reason why we want to do it is because when we want to define the addition component wise and multiplication, it is like how we define it normally for polynomials that we have already learned in high school. So a polynomial with this and with A's and B's, then you add them up, you just need to add the coefficient up. And it will be this polynomial. And when you multiply, then you just need to do the following, which is exactly like the same as the polynomials you've learned in high school. But now we don't treat it like it's getting any output, and it's just treated as an element that looks like a sum. And we see that Rx, so this is the notation for the polynomial ring. The polynomial ring is a commutative ring in which we can identify R as a subring of constant polynomials. And we already know that if R is an integral domain, then the leading term of a product of polynomials is the product of the leading terms of the factors. And for completeness, we shall just restate the proposition that we have proved before, that if R is an integral domain, then the degree of Px times Qx is the degree of Px plus the degree of Qx. And this helps us to show that the units of Rx must be the units of R. And so Rx is an integral domain as well. And proposition 2 states that if you have an ideal and you generate the quotient set where you take Rx over this I, it is no different from taking the quotient of the coefficients first, then you create the polynomials. In particular, if I is a prime ideal, then the ideal generated by I will also be a prime ideal of Rx. So you can just create a natural map from the polynomials to the new polynomial rings with the quotient as the coefficients, given by reducing each of the coefficients of a polynomial modulo I. And as a result of this, you can show that this map is a ring homomorphism, and the kernels are precisely the polynomials whose coefficients are elements of I, which is to say that the kernel is Ix, which is the ideal generated by I. This proves the first proposition. And the last statement follows that if I is prime, then Ri is an integral domain. This means that this polynomial ring will also be an integral domain. And this shows that if I is prime ideal, then I is also a prime ideal of Rx, because they are bijective, isomorphic to each other. It's not true that if I is the maximal though, then the ideal generator will be maximal. But we know that if I is maximal, then the ideal generated by I in X is maximal in Rx. So you need the extra X over here. Some common examples will of course be the reduction modulo homomorphism that we have already seen. which helps us to solve the Diophantine equations. And we can extend our polynomial rings to several variables by doing it inductively. This means that we consider the polynomial and n variables with coefficients in R simply as a polynomial in one variable, but now the coefficients as polynomials themselves. And so it's really just saying that is the set of all finite sums of these element terms. So an example will be shown over here. So the polynomial ring zxy consists of all finite sums of the monomial terms of the following notation. So this px and qx are elements of this polynomial ring. So you can see how the x and y's can either be together or separate. And then one has degree 3 and the other one has degree 5. So you just need to add all the powers and see like what's the highest. And so when we combine them, this will be the following. And when you multiply them, then you can actually see that it's still a polynomial of degree 8. So all the rules and propositions that we have already proven holds true. And now you can actually just see, you can actually view the last polynomial as a polynomial in terms of y, with the x as, with this as the coefficients where it has x term, but it's not important. So you can play with how you want to view it at different points in time to prove the question better. But what we're really interested in is polynomial rings over fields, and reason is because it gives us a lot of nice properties that we want. So when it's a field, then we can define the norm on this polynomial ring over field to be the degree of px. And one thing is that it will become a Euclidean domain. So you can actually do the division algorithm on this polynomial ring where the coefficients now come from a field. And really, the reason for that is you really need this to be inside the field itself. So an to be divided by bm. And you can just check the proof and you can see that we have already done it, a similar thing many times. So I'll leave it to you to read this proof yourself, but it shouldn't be too bad. But one thing to note is that there is now a uniqueness when it comes to the quotient and remainder, like how there is a uniqueness in the division algorithm for integers. And really that's because now you have a field and the degrees you gotta be unique. So I'll leave it to you to read the uniqueness over here. And so a corollary of this is just saying that if f is a field, then the polynomial ring over f is an PID and also be a UFD, because it's once you satisfy this Euclidean domain, a Euclidean domain is a PID and a UFD. And by the example above, we can already see that the ring ZX is not a PID, as we see that the ideal generated by 2 and x is not principal in the ring. And Qx is a PID because the coefficients all lie in Q. And next we'll talk about an important criterion for factorization known as Gauss' lemma. And it states that, so we have R, which is a UFD with a field of fractions F now. So we create a field of fractions. If we know that Px is reducible in f, x, in polynomials with coefficient f, then we will know that Px is irreducible in Rx. And the proof, take notes of some technicalities. So it's quite a short proof, but it requires some, you need to be clear on where the steps are. So I'll just go through it. the coefficients of the polynomials on the right hand side of the equation, so over here, are elements in the field F. And hence the quotients of the elements from the unique from R. So we can multiply a common divisor through all of them to obtain the following equation. If D is a unit, then the proposition is true, because we have found our factorization in R. So we assume that D is not a unit, and so it must be a product of irreducibles, since R is a UFD. And since P1 is irreducible, the ideal is prime, and so the ideal Pi will be prime in Rx as well, and as a result, you quotient it will be integral domain. And so we can reduce the equation to dpx equals to a prime x times b prime modulo pi. And this part will get cancelled out. And so one of these must be 0 since it's an integral domain. So let's say one of this is 0. And this means that all coefficients of a prime x are divisible by P1. And so this is the coefficients in R. In other words, D times Px equals to A prime times B prime, and we can cancel the factor of P1 from D. So we cancel the P1 from D, and from either A or B on this side. And we still have an equation in Rx. And we can keep doing this for every irreducible and cancel all the factors of D into the polynomials on the right hand side. And so then you'll be left with Px equals to Ax times Bx. And now these A and B are in the elements Rx. And so we are done. So you can take note of how we do it, and we really need the D in this case to help us by this common denominator. And then we'll just slowly cancel it out and we'll get the solution that we want. So what you need to take note of now in Gauss' lemma, after understanding the proof, is that if you are irreducible in the field ring, polynomial ring, then you are irreducible in your UFD polynomial ring as well. And you are reducible in your UFD polynomial ring as well. And so the elements of the ring are the units in this fx. And for example, 7x factors into 2 irreducible 7x. So 7x is not irreducible in zx. But you can see that 7x is a unit, is the unit 7 times irreducible x. So this means that 7x is irreducible in the quotient one. And so now there is some sort of difference between the irreducibles in R and the irreducibles in the fx, the field. So what we want to take note now is that you let R be the unique factorization, F be the field of fractions. You let a polynomial be in Rx. Then you suppose that the GCD of the coefficients is 1. Then Px is irreducible in Rx if and only if it's irreducible in Fx. So here is reducibility criterion in Gauss' lemma. Now you want to talk about the irreducibility. And by the Gauss' lemma, we know that if Px is irreducible in Fx, then it is also irreducible in Rx. And conversely, now we assume that the GCD of the coefficient implies that if it's irreducible in Rx, then Px equals to Ax times Bx. Neither A or B are constant polynomials in Rx. And this means that if these are not constant, then the same factorization will show that Px is reducible in the field of fractions as well, completing the proof. Hence, this shows that Rx is unique factorization domain if and only if R is a unique factorization domain. And the corollary of that, and this just follows from corollary 6, and corollary 8 follows from theorem 7, because now we know that R is a UFD, then the polynomial rings over arbitrary number. So this is just one variable, but you can just keep doing it inductively and just show that it's also a UFD over arbitrary number of variables. Here are some examples for you to look through. And that's all for this video on polynomial rings, where I introduced to you more about this example and how this irreducibility plays a part. So you can see how the importance of reducibility and irreducibility are taken care of in the polynomial rings. And next time we will see more examples and more criterions for irreducibility in a ring, in a UFD. So I'll catch you in the next one. See you.